Yesterday we started looking at error correcting codes, and today we are going to see how the error correcting codes are used to detect errors. Oh, sorry, I'm not. I think I need to share. We started looking at error correcting codes, and we will continue looking at how these error correcting codes detect errors and correct at the receiver. At the moment, we will not go into how you construct the generator matrices, because in this case we are using generator matrices. But later, but of course, um, we can be able to get some of these matrices we are using from constructing BCH codes. Don't know about BCH codes because most of what we are going to be doing after um, after looking at how the generator matrices and their corresponding error checking matrices are used to first um, create the code words and then to check whether those code words have errors at the receiver. Yeah, you create the code words from the generator matrix, and then you use an error checking matrix at the receiver to establish whether there are errors or not, and subsequently correct those errors. I thought that's the best approach instead of the other way around, where you learn the science of creating um, generator matrices or constructing generator matrices, and then um, use them to correct errors. I thought this is the best way. Once you understand how they are used, now you get curious to know how exactly are they constructed. And we are going to concentrate on mainly the construction of BCH codes, which are built on the backbone of fields, especially the Galois field. So, uh, so what we are going to do, we are going to consider mainly, we are going to look at a case where we are constructing linear block codes and more so systematic. Systematic is the one that contains uh, um, systematic is the one that contains the first part contains all the message bits, the second part contains the error checking bits, or rather the prefix is the message bits and the suffix is error checking bits. They are not intermixed because you can use a generator matrix such that they are mixed. Yeah, that you can have some error checking bits inside in the first half of the first part of the n digit code word. Yeah, and we are going to see that to create this systematic code, because if you create this code where all code words the first part is a message bits, you need to use a matrix which has a part, which that first part, that prefix part of that matrix, if we can call it so, is the identity matrix. Yeah, it will become clearer once we use an example. So we said we are going to do the binary block code, and our example, the examples you are going to use are linear codes. Yeah. Now, what does linear codes? Linear codes, it means you can create when you make, if you take any two code words and do the modulo 2 sum, then you get another code word. To get another code word, when you talk about code word, it means you are talking about a valid code word. Let's be very clear about that. And I think somebody asked me about validity. What we mean by valid code words is, you see, if you have these 4 bits, if you have these k bits, and then you multiply this with if you have this k bits, a row vector of k bits, then you multiply it with a k, this is k by n. Yeah, this is a k by n matrix. It has k rows and n columns. Then you are going to get a code word of n bits. Yeah. So this matrix is the one we are seeing. It must have a part of it as the identity matrix, so that it gives us systematic code. Yeah. And this is what it gives us systematic code. You can see, like now, this is this. Well, in this particular case, well, I think the best definition, I said, for systematic, that can be confusing depending on the code one I've used here. I said for systematic, you need the first, this to be the k message bits in the code word. I think maybe I can correct that and say that what you need is that either the prefix or the suffix are just the message bits, but they are not intermixed, because you can see, like in this case, is the opposite. Yeah, you can see in this case is the opposite. Our message bits are these ones, because this is a message. It means this one, the identity matrix, we have 2 matrices which are concatenated to create this generator matrix. And these 2 matrices, for this case, this is the identity matrix of order k. Yeah. Yeah. So let's do the particular example. I think some of these. So if you say a block code is linear and systematic, what you mean? It must be very clear that either the prefix or the suffix is a message bit, and also that you can create, that covers the systematic part. The linear part means that if you add any 2 code words, they produce a systematic code word. Now, what I was trying to, no, I mean, no, they produce another code word. And when we talk about a code word in a code, we actually mean a valid code word. Yeah, because you can produce, you can have other codes which are not valid. Yeah, you can have another arrangement of these things which are not valid. Yeah, so if you use this particular generator matrix, and these are your messages, necessarily your code words will be this. This 16 will be the code words. So long as the message is one of these, and it has to be one of these, because when you arrange 4 bits, these are all the ways you can arrange the 4 bits in. And when you use this particular matrix on these message bits, it will necessarily produce this code, or rather this group of code words, which we call a code. So if you arrange these ones and zeros in any other way, which does not belong to this 16, that one is an invalid code word. Or rather, it's not a code word, it's invalid, because a code word means it was produced by this particular generator matrix. So it is invalid. And that actually is the main, I mean, that's what makes us be able to detect errors. That all we have to do, you remember what we said about for example, the case of binary, I mean, of simple detection, and simple parity error detection method. We said the receiver just needs to find out whether what you are getting is supposed to be the parity you are expecting. So if it is odd parity, what you are getting is odd, has an odd parity, has an odd number of ones, and is even is a if it's for even parity, then it has an even number of ones. Now, in this case, the detection is based on the fact that if you can be able to determine that whatever you got is not part of this, then you have discovered there's an error. Because whatever, if you want to send this message, you must send this. So if you want to send any 4-bit message, you must send one of these. Yeah, it cannot be anything else. Anything else means have come out because of an error. Yeah, and that's basically the how these error correcting codes detect the errors. We are going to see how they correct, but that's how they detect the errors. Yeah, so that's what I was saying. If you arrange zeros, because you have 7 bits, you can see we are moving. Actually, that's how we put it. We are moving from a 4-dimensional space to a 7-dimensional space. Yeah. So the moment you create this, then it is easy to detect your errors at the other end. In that, whatever will come out of this, again, I'll repeat, but whenever you send this, it means necessarily this is what you send. But what you receive may not be that. It may be different. Now, one thing we are going to see is this thing is a linear code, in that if you add any two code words, you produce a code word. Yeah. If you add any 2 code words, you produce a code word. So if you add this and this, of course, that's the trivial case, we are going to get this. Yeah. If you add this and this binary 2, of course, I mean modulo 2, you're going to get another code word. In fact, what are you going to get? You're going to get 1, 0, 1. If you add these two, you'll get 1, 0, 1, 1, 0. Oh, 1, 0, 1, 1, 1. Ah, there's another 1, 0, 0. And actually, this will be a code word somewhere. Let's see what it is. 1, 0, 1, 1, 1, 1, 0. Yeah, you get this one. You see, you have added these two, you got this one. So if you add modulo 2, any code words, two code words, you get a code word. It means it will be one of these. But again, what can be sometimes confusing, to get this linear code word, you're going to find that the generator itself, the generator matrix itself, these have to be linearly independent. The rows of this matrix, actually, this is a generator matrix. The generator matrix we have used here, you can see it has got, to get this code, we have used this generator matrix. You can see it has got two parts. And one part is a K by K identity matrix, or rather what we call the K identity matrix. So this is the one that is giving, of course, if you multiply out, you're going to find these bits will just be repeated. If you have, for example, A, B, C, D, these are your bits. Yeah. Although of course we don't put these commas. I'm just putting commas to, they're just right the way you're supposed to write it. If you have A, B, C, D, it means once you multiply this, necessarily, because this will be the first part, will be, let's forget the first part of what you get, but the last part will be this. Then the others are 0, so that will be A. Then the second part will be this is 0, so only B is there, so this will give you B. The C part, of course, A will be 0, B will be 0, and D will be 0, so you only end up with C. And the last part is the same. A will be 0, because the first will be 0. This will be 0, A times 0, B times 0, C times 0, D times 0, and D times 1, sorry. So this is what gives you the systematic. The fact that you have got this part gives you that systematic code. This will be different. But what I was trying to tell you is, so that you don't get confused about the linearity and non-linearity, because although these are what do you call it? Although these are linearly independent rows, this matrix must have linearly independent rows. It means you cannot create any row by adding two rows. But the code they produce, they are linear. Yeah, they are linear in that you can add any two to get another one. But the rows of the generator matrix must be linearly independent. Yeah. So if you add any of these two rows, you're not going to get another row, and you can try it. Yeah. What else did I want to? Let's see. I was trying to see whether this is. Yeah. Oh, okay, I was trying to see. So this matrix, the way the matrices are is very important. This, you see, this matrix. I think for this matrix, this is still linearly independent, but this one is slightly different from this one. They are linearly independent. So the code which you produce with this one would be cyclic, because you can see we are, the rows are just, we are just shifting. When you shift the base in the row to the right, we create another row. The 1101, 1101, 1101, 1101. So this would create also a cyclic code. So apart from it being linear, this would create cyclic. This one does not create cyclic the way they are organized here. Yeah, is but anyways, so but we will come to cyclic. But I thought I can mention that at this juncture because I will be talking about cyclic somewhere. So that's how you create your codes, yeah, or your code words, yeah. And yeah, I've mentioned cyclic here. So a cyclic code is a block of code where circular shifts of each code word gives another valid code word. And that's what I was trying to show you that, and actually, this, I want to check whether this cyclic, but I think from its, I was trying to check whether that will be cyclic because this is not produced by a cyclic. I don't think, oh, maybe if you do it again, you can get this, yeah. So, but an example of a cyclic code is this one here. Here's a cyclic code 110. If you produced code words, if you had a method of producing these code words, so and you got these code words, now you can describe this as cyclic code. I've used an example of only 3 bits. Yeah, this is a cyclic code because if you shift this to the right, 0 will come here, you get this. If you shift this to the right, 0 will come here, you get this. And if you shift the base to the right and bring the last one to the front, you are going to get another code word. That's what we mean by cyclic codes. And we are going to see later why we are mentioning it, because we are going to do a lot with the BCH codes, which are cyclic. Yeah. So cyclic codes, of course, they are used a lot because they are easy to implement. Yeah. When you implement cyclic codes, it's very easy because you're just going to use flip-flops. It's very easy to implement cyclic codes. Now, so you have created your code words. I hope by now everybody has seen how we are creating the code words. It's simply multiplying, just multiplying the message, with the generator matrix. So in this case, to get this, you multiply this with this generator matrix. Yeah. If you multiply any message sequence with this generator matrix, you get the code word sequence, the output sequence. Yeah. Yes. I think that one you can find out for any of them. This is how you produce this. Now, once we do that, we need to have an error checking matrix. Yeah. Now, error checking matrix for our case, for a linear, because we are dealing with a linear here. Linear systematic codes are not the only codes. There's some codes which are nonlinear. They can still generate a code, but they are more difficult to deal with. Yeah. Uh, there are codes which are cyclic. There are codes which are linear and cyclic. There are codes that can be linear, cyclic, and systematic. So in this case, we are dealing with a linear systematic code. Yeah. We have used the linear systematic code case to demonstrate our error detection and correction. Because of um, it is easy to generate, for example, easy to generate the error checking matrix. Yeah. Because at the end of the day, you want to be able to check the error checking matrix. Yeah. Which you are going to use as the receiver to check whether there is an error or not. So for the linear systematic code, you have this generator matrix, which has got a first part, which you call the P matrix. This is like I won't call it a generator polynomial, but just a pattern of zeros and ones. The P matrix, and then you have a K by K identity matrix. This matrix like this one. Yeah. So you have a K by K identity matrix, and then of course you have a K, an N minus K, or rather a K by N minus K P matrix. Yeah. A K, because this is K, and this is K. So, and this must be N. So this is going to be N minus K. So to make your K by N generator matrix, you concatenate your K by N minus K pattern with a K identity matrix. A K by K identity matrix, or what you call is an identity matrix of order N. Yeah, okay. Yeah. So that's how you create this. Yeah. So in our case, that's what we have. So let's see. So now from that, you can be able, for every this generator matrix, there exists another matrix which we call the H matrix, the error checking matrix, the parity check matrix. We call it parity check matrix, such that G will give you 0. That matrix, if you multiply this G matrix with that H matrix, you are going to get 0. And that is the matrix we are going to use for checking errors. Yeah. So our case, that is the matrix we need. But that matrix for systematic code is very easy to create because it is simply IN minus K concatenated with P transpose. Yeah. IN minus K concatenated with the P transpose. Remember, N minus K in this case is 3. Yeah. In our case, N minus K is 3. This one here. So you need to have a matrix of N minus K. So in our case, the matrix we are going to have is this one. You see? An N minus K identity matrix by an N minus K by K, this other part, which is actually simply, this is simply P transpose. Yeah, because P, remember P in our case is this one. This is P. That is P. So this is our P transpose. Yeah. And you can see it's transpose because you can see this, like this was going to, this was, if you check here, this was P00, P01. Yeah. If you check here, the matrix is P00, P10. Yeah. So the before it was, that was P00, P01, but now this is P10 because these are a P transpose. It is the same matrix here but transposed. Yeah. So that's how you create the error checking matrix. And for actually, if you check these matrices, if for example our case, we have got these two matrices. We have I was trying to see whether I can. Oh, sorry. I think can you actually you can't even multiply with H. Sorry, that is misleading. H transpose. Yeah, because if you are multiplying two matrices, then now the columns must be the same as the rows of this. Yeah, so this has to be the H transpose, not the H. So G H transpose is equal to 0. Said about that. You can multiply G and H because they have the same number of columns. So the number of columns for this must be the number of rows for this. So it must be the H transpose. Yeah. So far, is there any confusion before I proceed? Because if you get confused at the stage here, then the rest will be, you don't understand the rest. So it's good to understand where we are coming from. For the linear systematic matrix, linear systematic code, for the linear systematic code is very easy because you have one part which is the identity matrix, and the H is just made of and now you have to be very careful is if you have it in this form, identity matrix is on the right, then this n by n minus k identity matrix must be on the left. Yeah, and vice versa. If you had used identity matrix on the left so that your systematic code starts with the message bits, your code word starts with the message bits. Yeah, because ours does not start with the message bits, it starts with these are the error checking bits. Yeah, so the error checking bits, then the message bits, because of our generator matrix. But doesn't mean that this generator matrix can also be the other way around. Yeah, we can also have a generator matrix where this comes first and this follows. Now, if that happens, then also the order of this matrix changes. Yeah, I'm saying that because the confusion I see a lot. You can see ours there was this one. I think it was the transpose of this 1 1 0 0 1 1. I'm creating our generator matrix reverse from this. This 0 1 1 1 1 1, and the last one is 1 0 1. I'm just transposing this. Then I'm saying this is our generator matrix. Oh, sorry. 0, and this is sorry, 0 0 1 0 0 0 0 1. Yeah, that is our, I'm putting them side by side so that you can see the relationship. So we are saying this is our G, And for this G, and you know that this G multiplied by this matrix should give us 0. If you multiply these two matrices, it will give that. So we are saying this matrix, you can see the identity matrix is here, but the I minus K, I n minus K identity matrix is here. Very important, because if you don't do that, if you put them on the same side, it will not give you what you expect. So now all of us, I think we can be able to generate the parity check matrix when you are given the generator matrix. Yeah, it's simply, if this is IK matrix, yeah, or rather K by K matrix, all you have to do is this becomes IN minus K concatenated with the this P transpose. This is P transpose. Yeah. So does anybody have a problem with that? Mark Murege? You don't have a problem with that. Okay. Now, before we come to this parity check matrix, there's something I wanted to mention, and I can see like this. Yeah. Now, did I leave something? Ah, yes. The most important thing about error checking is something which we call the syndrome. So what happens is, if you multiply any of these, what do you call it? Any of this code word with the error checking matrix. I said if you do the generator matrix with this, you get 0. But if you multiply any code word among these with this, with HT, you get 0. And we can do with an example. Let's do with an example. Let's pick any of these code words here. Let's take the one you can remember easily. Which is one I'm going to remember? 1001 011. Trying to get where the space are. I can do here 1001 011. I think that's the one I've picked. That's a valid code word. Anyway, you can even check whether it's a valid code word because it will give us 0. Let's use. I think we know that matrix. It must be starting with 1 0 0 0 1 0 0 0 1. This other one will be the 1 1 0. Actually, it will just be, of course. Yeah. Because when you put H transpose, of course, this will just be, because this becomes now P transpose. Yeah. So eventually, I think to get H, you transposed the P, and now to get H transpose, it means you are transposing the P transpose. So it becomes the original P. Yeah, isn't it? Because to get this H, you transpose P. Now to get H transpose, you transpose P again. So here it will simply be 1, 1, 0, just like the generator matrix. This part, P part. 1, 0, 1, 1, 1, 1, 1, 1, 1. What has happened? Where was I doing the multiplication? Ah, 1, 1, 0. I think 0, 1, 1. 1, 1, 1. My memory seems to be, can't memorize something for a few seconds. 1, 1, 1, 1, 0, 1. Yeah. Uh, 1, 0, 1. Let's see what that becomes. So this is 0. So this is 1 times 1. You know how we multiply matrices. 1, that is 1. That is 0. That is 0. That is 1. So you have 1 plus 1. That is 0. That is 1. And that is 1. So you have 1 plus 1 plus 1 plus 1. That is 0. Yeah. Yeah. Because 1 plus 1 is 0, and 1 plus 1 is 0, and then 0 plus 0 is 0. So anyway, if you add even number of bits, the result is 0. If you add that odd number of bits, the result is 1. Yeah. For module 2 addition. Yeah. Then this, the second one, now this will be, I did the first one first, you can see how we multiply. So this will be 0 plus 0 plus 0 plus 1. Yeah, this volume is 1 plus 0 plus 1 plus 0. So it is 1 plus 1. Now, this is 0 plus 0 plus 0 plus 0 plus 0 plus 1 plus 1. So 1 plus 1 is 0. So when you multiply this code word with H transpose, we call that the syndrome. The result is called the syndrome. So the syndrome of this code word is this one. Yeah. The syndrome of this code word is this one. Now, what is most important is any of these code words, their syndrome is 0. It means if you get any of those code words, then the syndrome is going to be 0. What does that mean? It means since for the case of 4-bit messages, the only possible messages were these. If you get anything else, it means there's an error. If you get anything else, it's an error. And getting anything else means the syndrome is not 0. So then what the receiver does is simply get what it has received. That code word which we are calling here R. R is the received vector. Yeah. And this one, sorry, this is H transpose, not H times T. So we are saying the syndrome of R is defined as R dot H transpose. Say the syndrome is 0 if and only if R is a valid code word. If S is not equal to 0, it means R is not a valid code word. It means R is not one of these. Now, for this to work, there are a few important rules here. And it comes from something if you have two sequences, this is what I call Hamming, who discovered this, so we call it the Hamming distance. If you have these two vectors, the Hamming distance between these is the positions, is the number of positions where the bits are different. So we have 0, 1, 1, 0, 1, 1. We have 1, 1, 0, 0, 0, 1. So here, this bit is different. This is the same. This bit is different. This is the same. This bit is different. This is the same. So for 3 positions, the bits are different. So the Hamming distance of these 2 vectors is 3, which you write d v1 comma v2 is equal to 3. So it's a distance, but we normally call it the Hamming distance, from the fellow who discovered that this Hamming distance thing is a very crucial thing in error detection. And it makes a lot of sense, because the Hamming distance is very, very important. It means, why is it important? If you have got these 2 vectors, the only way you can create this vector is by changing 3 bits. Oh, yeah. It means you change this to be 1, this to be 0, and this to be 0. So you have to change 3 bits to create this vector. So Hamming distance is very important. And I'll tell you why it's important. You see, to detect errors, it means if there's an error, to detect it, it means what you have received is none of these. But now you see that argument can be a problem if one of these, you send one of these, maybe you send this, but bits change, it becomes something else here. Some bits change, so it becomes something else. Then you cannot detect the error, because the syndrome will still be 0, isn't it? If something changed, the syndrome will still be 0. Just like you are saying in the case of the binary or the simple parity bit. If 2 bits change, then the system will not work, because you are going to get the parity you are expecting. And that's what we are saying here. If bits change such that they create another code word, then the system will not work, because the you're still going to get zero syndrome. So it is very important that for that to work, then the the distance must be such that you cannot create a code from the other one. And you say, so to detect that one error, you need a minimum distance. For this one, we need a minimum distance, and the minimum distance is required is 3. It means the distance between any of these codes, excluding the zero code word, because the zero code word, you can see, like, no, you're not even excluding, because the minimum, we are talking about the minimum distance. I'll tell you when we exclude that. We are talking about the minimum distance. So the minimum distance of this is 3. So if you take any two codes here and you compare them, you're going to find that they differ in at least 3 places. What is this? What is it telling us? It means if if one bit is in error, it will produce a code word that is not here. If 2 bits are in error, it will produce a code word which is not here. So you're going to detect it. But if 3 bits are in error, it may produce, it will not always produce, it may produce a code word which is here. And therefore, you can. So this code can detect 2 errors, but we are going to see it cannot correct 2 errors, they can only correct 1. What we mean is it can correct in this, it can correct 2 bit errors. It means if 2 bits change, it can correct. It can detect. Sorry, it can correct. It can detect. When it comes to 3 errors, no, you never know. Why we are saying that, of course, for example, if this change 3 bits, very likely to come to one of these. Yeah, but it also depends on which bits change, because you can see the only ones which are 3 which have got we can talk about it. Now that is the distance. But when we look at a code alone, there's something else. The number of ones and vector. Distance, you're comparing 2 vectors. So the weight of this is 3. The weight of this is 4. But how many distance between the two is 3. What does that have to do with our code? A lot. Because the humming is the minimum weight. If you exclude the zero code word. Of course, why we are excluding? Because you can see this. If you include it, include it, then the minimum weight, because because this has a minimum weight of 0, so you can't include this. But if you exclude this, the minimum weight is 3. It means all of them have 3 bits or more, 3 ones or more. Yeah. So why this is important is because if you want to find out the minimum distance, instead of comparing every other bits. I mean, every other code with every other code, which is going to be, I don't know how many comparisons are those. I think it's n into n minus 1 comparisons. Yeah, I think so. I think, okay, yeah, I can do with a simple case. Let me do with a simple case of on A2. So you have to compare this with this, compare this with this, compare this with this, then compare this with this, compare this with this, and then compare this with this. Yeah. Oh, yeah, it is n into n minus 1 or n plus 1. Is it n? I'm doing how many comparisons? 6 comparisons. And the beta are 2, so it is n into n plus 1. It's not minus 1. Yeah, I think generally those are the comparisons you need to do. I think I can extrapolate that with this. Yeah. But instead of doing that, all you do is get the minimum weight excluding the zero code word. I hope everybody understood that one. The relationship for this code, a linear block code, between the minimum weight and the minimum distance. Because the minimum distance is important so that you don't generate, you can't, it will be so difficult to generate a code word during transmission, because what you are saying, that channel is so bad that for 7 bits it is going to change 3 bits so that it can create another valid code word. Because once you create a valid code word, then the system does not work. That's what we are just saying. Because it will produce a zero syndrome. So the receiver will think that what I have received is the correct code word. Now, what else? So you have understood the concept of the minimum distance and the minimum weight, because they are now. I'm just going to see whether I've left anything. I've not left anything. I think we are going to do some tomorrow. On Wednesday, we can do an example or two. Let's finish this. So now, if you have this is a syndrome. For example, this is what you have received. I think if you look at this, it is not, and you can see because this is a syndrome. It tells you this is not a valid code word. For the code word, for the code words that were generated with the generator matrix that pertains to this parity check matrix, it means it's not a member of that code, or rather, it's not a valid code word. So suppose this is what you received. So the syndrome will be this. Yeah. So that you can do the math, and you're going to get this. Now, this is very important because this one tells us something. We can use it to decode, to know now where was the error. Because the presence of a syndrome which is not zero, that is error detection. It has told us there is an error. But how does it tell us which error it is? Then I think it will become clear if I explain this. Yeah. So here is your here is your um, message sequence, 4 bits, and this is your generator matrix G, and this is your uh, a code word. Let's call it C. Yeah. So if you multiply this, it will be this is what you are going to get. And of course, you can see this is what you are going to get. You can see this C1s is related to the digits like this. This is how they are related. Yeah. And to make sense, because you see, to get C, you multiply when you multiply this with this identity. So the first 4 bits will just be D1, D2, D3, D4, which is this one here. Now this one will be D1 plus D2, D3 because of this will be 0, so plus D4. So that is that. Then this other one will be D1 plus D3 plus D4. And C3 will be D2 plus D3, D4, because D1 will be 0 because of this 0. Yeah. Now, I don't know that yeah, it's good to know that. Well, the importance of this is also easy when you are doing your arithmetic. With a systematic code, actually, knowing this is very important, because with your systematic code, if you are given a message and then you're supposed to do the code word, you don't have to do a lot with this particular one. If this is your matrix, all you have to do is this math. So you just, if it's systematic, of course, for example, you're given, let's say you're given 1, 1, 0, 0 as a message. Of course, now to generate your code will be to generate C1, because the 50 bit is a C1, will be D1 plus D2 plus D4, which is, so this will be 0. 1 plus 1 modulo 2. Then the next one will be D1, which is 1, plus D3 plus D4. So this is 1, because this is 1 plus 0 is 1. The last one will be D2 plus D3 plus D4, which is D2 plus D3 plus D4, which is 1 plus 0 plus 0, which is 1. So this will be the code word for 1100. And I think you can check from here. Of course, in this case, it is the other way around, because 1100. Let's see where 1100 is. This one. It is here 1100. So it will be 1. Oh, it will be 1100. Yeah, it will be 1100. Oh no, I think it changes when you change this. When you change this order, it changes, because this is not 101, 1100. Oh no, because this code word is not generated with that. You see, the generator matrix are different. So sorry, it cannot be here, because our generator matrix is different. Our generator matrix, this is coming fast. So sorry. There's a, I just did exactly what. There's a problem with this, because my generator matrix Oh yeah, this cannot be correct because my generator matrix is not the generator matrix in the example, so it cannot be that. The generator matrix is different. You see, our generator matrix is the other way around. That's why I was trying to do this and it's not coinciding. Yes, it won't correspond because I've used a different generator matrix where the identity matrix is coming first and the P is coming next. So this one would not be, the code words will not be the same as this when you change this. So you have to be very careful. As you have just seen, that this code word is not a valid code word for that because we are using a different generator matrix. But what we are saying, why it becomes important, how we do the syndrome decoding. If you have the parity check matrix, you can either do this, to get a syndrome, or you can do this. It's the same thing. Yeah, there is no difference. But with what I want to demonstrate, is better that you do it this way because I want to talk about the columns of the parity check matrix. Yeah, it will be the same thing if you multiply that the received vector with H transpose will give you the same results like if you multiply H with R transpose, yeah, where R is the received vector. It will give us the same result, only this one will be a row vector and this will be a column vector. And we are more interested in the column vector because it has a relationship with this. Yeah? You see? Now, and please, if you don't understand, ask a question. But I keep on insisting because unless you ask questions in an online class, you'll get lost. For the simple reason that I play that part. I know I look at your faces when we are in class and you know he didn't understand or she didn't understand. But here, purely, is you to help me. You don't understand, ask. And when I'm talking, sometimes my words might not come out very clearly. Please ask. Yeah. I'm aware sometimes I'll get excited and my words will not get through very well. So, in the event that that happens, ask me. I'm aware, so you'll not be telling me something I don't know. I will not get offended. So, are we, Edward, Luma? Are we good? Are we okay so far? Edward. You see, Edward didn't care. Yes, Soba Yusuf.
I'm okay so far. I'm following.
Yeah.
In the generator matrix, where does the P matrix come from?
Oh, the P matrix. Oh, how do you get this P matrix? Yeah, that's why I say we have not gone to the construction of the P matrix, but you can see the combination what is important is this P matrix combined with the identity matrix. Concatenated, this is a P matrix. This is a P matrix. So the P matrix can be, now for systematic code, it will either be come before the identity matrix, or it can even come after the identity matrix. Is a part which is not, is the part of the generator matrix which is not an identity matrix for a systematic code. So now, what is important is this generator matrix, the rows must be linearly independent. These rows, not the columns, the rows, these are linearly independent. Where linear independence means you cannot get any row by combining any two rows. Of course, linear independent is more than that. But if you are dealing with GF2, where you only have, where you are, the field is only a 0-1 field. Yeah, we are going to look at the fields later. If you are dealing with the Galois fields, the field of where you have only 1 and 2, I mean only 0 and 1, sorry. Then it simply means if you add any of this modulo 2, you will get another one which is here. Yeah. So that is the only important thing. Not of this or this, but of the entire row. And this does give us that. Yeah. So this is the part, this is the P. This P. And this is the one which we transpose. And of course, you can see once we transpose it, it means now the rows will be n minus k. And for you to concatenate two matrices, it means the rows must be the same size. Yeah. So once you transpose this, it means you concatenate with an I n minus k matrix, because the rows of this is n minus k. So you transpose with n minus k identity matrix. Did I answer your question? Did I? If you still didn't get it, don't accept. If you didn't get it, it's still.
So like, is it something that we're like supposed to, I guess, take it as it is, or we're supposed to generate?
For now, just take it as it is, because later we are going to see that I think even what we are using can be generated through BCH construction, which we are going to do in detail. But for now, just take it. You are given a matrix. So if you are given a question like this one, you'll be given either the H matrix or the G matrix. Yeah. But later, of course, we are going to look at the detailed construction of a BCH code, and I think this is a special case of a BCH code. Yeah. Although, of course, the BCH code we are going to generate, it will be giving us generator polynomials, but you can also create generator polynomials, generator matrices from generator polynomials. Yeah. So for now, take it the way it is. Take it that you have been given. So of course, if you are given this and you are told it's a systematic generator, you don't even have to be told. The moment you see I of k is part of it, then you know that it's a systematic binary code generator. Yeah. Binary block code generator. Yeah. Is that okay? Don't worry, we are going to do the construction of but we are going to dwell again on the BCH code, which are important because you can determine how many errors you can correct and detect. But this code can only detect 2 errors and correct 1 error. it cannot correct 2 errors. But it can detect 2 errors. What we are saying is if there are 2 errors that can be detected, when there are 3 errors, they can't be detected because you may produce another valid code word. And the moment you produce a valid code word, then the system does not work. Okay, good. Now, this is where I was. I was here. Now, what you are saying, if this column vector here, which is received, the received vector code word, or the received vector transpose, or the received sequence transpose, then it means that you'd get the syndrome as 0. But if you had a valid code word, now we want to see why you're able to correct only one error, only 1 bit error. If you have a valid code word contaminated by an error vector of 1 bit. So the error vector, of course, if it is only 1 bit, can be in error. It means the error vector can be that, it can be that is 1. It can be, you can see all the possible error vectors. I started from the bottom. It's only 1 bit error. Yeah, you can see why you're able to check 1 bit error. 0. So I started from the bottom instead of from the top. You can see where we are headed. So it can be 1 bit error. So long as this is 1 bit error, if you multiply these 2 matrices, so you multiply this matrix, because you see, if you have something, let's assume we got a valid code word, then you add this column vector, it is going to change only 1 bit. And of course, that will be, this is the received code word. So we are saying the received code word, it must be some valid code word with 1 bit error. So you have an error vector, one of these error vectors. Yeah, there are another 3 vectors. I can even do it here. 0, 0, 1, 0, 0, 0, 0. Then you can have 0, 1, 0, 0, 0, 0, 0. Can have 0. No, can have the other one is 1, 0, 0, 0. So we are saying the error vector can be one of these. Yeah. So long as it's one of these, or rather, putting it another way, so long as it's only 1 bit in error, because again, this does not work when 2 bits are in error. So long as 1 bit is in error, you'll be able to correct. If 2 bits are in error, you'll be able to detect, but you can't correct. Yeah. But if 1 bit is in error, you can correct. How do you correct? This is what we are coming to. So if your received vector is a combination of the valid vector with 1 bit error, which means only 1 bit has changed, then if you multiply this with their respective column vectors, which means the valid code word transpose and the error vector transpose, which now is this one, then multiplying this and this will give us this, And multiplying this and this will give us this. So what we are saying is, since this is 0, it means this depends only on the error vector. Yeah, because so it means your syndrome depends only on the error vector, because this one is 0. Yeah. So this only depends on the error vector. What you get here depends on the error vector. So it means it can actually give us what the error is, because it depends on the error vector. It depends on which error vector is it here, which means it can tell us the position of the bit. And I've not shown here. So in this case, if you did your syndrome and you got this, it means your error is in position 1. Yeah. If you got this, your error is position 2. If you got this, your error is in bit position 3. If you got this, your error is in bit position 4. If you get like that. So it means by simply getting the syndrome, you actually know which bit is in error. And in error correction, the moment you know which bit is in error, then you can correct the error. So what the receiver does, it takes the syndrome, then it has a lookup table. It has this lookup table. This lookup table tells us, oh, if you get this syndrome, that is bit 1. If you get this syndrome, it's bit 2. Yeah. Maybe, let's call it normally, like naming, okay, let's call it bit 1, bit 2, bit 3, bit 4, bit 5, bit 6, bit 7. So you have a lookup syndrome, a lookup table that tells you that if you get this, then what the receiver does, it has been told which bit is in error, you just flip your bit. So is it clear to everybody how syndrome decoding is done? Because this syndrome decoding, establishing where the error, which bit is in error. So you can see with this one, not only are you able to detect the error, you're also able to correct the error. But it is limited to correcting only 1 bit errors. It can only correct when 1 bit is in error, or detect when 2 bits are in error. What it is telling us is if 3 bits are in error, you won't detect. And obviously you won't correct, because you won't even detect there's an error. So you will not even make an attempt to correct. So the system will fail. And sometimes the system can fail. Yeah. But again, we are saying a system that changes 3 bits is pretty bad. But what happens is, when we expect a lot of errors, where we expect a lot of, let's say, a lot of errors, which normally we also call them burst errors. Burst sometimes is used to mean all the bits next to each other, but even when you have more than 1 bit where you want to check, where you can only check 1 bit, then you normally call it a burst error. If you have too many errors, in that particular block. Although the real meaning of burst error, it means the bits are next to one another, but they need not be next to one another. We also use burst to mean there are too many errors following one in a small space. They are not random errors. Because random bit errors they can be apart from each other, but if they are next, it means something is wrong. For example, a scratch. Because error checking is also used for storage other than communication. So if there's a scratch in, let's say, like the CDs. So whatever error checking, whatever encoding you do, or coding for errors you do, you must take care of those kind of errors. So we are going to see later that you use error checking mechanisms which are capable, error checking and detection mechanisms that are capable of correcting multiple errors. And that's where BCH codes become very important. BCH and also codes almost built on the same finite on the same theory, concerning the same theory, Reed Solomons are used especially in CDs. They have been used in communication between satellites and the Earth, where you are expecting there is likely to be a lot of interference. Yeah, you can have out of burst errors because this one of detect one error in such circumstances may not detect the errors. Yeah. But again, remember that these systems are mainly used to detect I'm just weighing whether I should say it at this particular point because no, but maybe I can say it because I think we are going to look at it again, but I'm sure you have, when you did introduction to computers, or I don't know what you call it here in your course, whether you call it computing for engineers or foundations of computers. So sometimes you touch computer networking. You must have looked at the OSI model, the 7-layer model. I think somebody said that you have done it, eh? So there's what we call the layer 2 model. I mean the layer 2 error checking. So this error checking is normally layer 2, or rather is done at the link level. Yeah, I think I attempted to talk about that at the beginning, and I think it's good to talk about it because it gives you the whole picture. It gives you the whole picture of how serious error checking is taken, because you don't want to accept your code sequences, because in digital, or rather even in computing, in a digital, whether it's digital storage, digital communication, the meaning, or rather the information, is in the arrangement of the bits. So you don't want bits to flip and not detected, because again then the whole thing loses meaning. If bits are flipped and then your mechanism does not check that, then that is serious. So what you find is, if let's say like two computers are communicating with each other. I'm going to into this so you can appreciate error detection and correction. A is communicating with B. So first, you choose the route. Yeah. And again, we'll come to that. Sometimes you can choose the entire route before you start translating. Yeah. Or you don't have to choose the route. You just start transmitting because your packets have got your packets a part of the fields is a part of the field is a destination. Yeah. Where, Sherry? Have you come so far? Have you come across packet communication in some unit? Because unless I make assumptions.
I can't exactly recall.
Oh, you can't recall. Yeah. Thank you. But the third part of this is just the way it's organized in the course outline. Maybe I should have started with it. So as you appreciate the computer communication. All digital communication today is in the form of packets. And of course, that can be pretty confusing because when you say packet, somebody does try to visualize how a packet moves from here to wherever it's going. But that's not what a packet means. A packet just means your data is arranged in packets, but of course, when it's being transmitted, it's transmitted bit by bit. So it will be a packet. That packet will be called a frame. Between here and here is a frame. So that frame, but when it goes to the wire, the frame goes bit by bit. So again, the frame is reconstructed here. So you have your frame. It comes bit by bit by bit. Once it is fully transmitted, so it means you have some buffers here which are storing your frame. You look at the frame again, and you find out where am I supposed to go, because you are going to be looking at through all the bits. It tells you where you have to go. So you can have a system whereby that decision is made at every node. Yeah. You can have a case whereby the frame is made at every node. I mean that decision to forward is made at every node. And of course, we call that one connectionless communication. You don't make that decision at the beginning. It's connectionless communication. Or you can have communication whereby the path is determined even before you start transmitting. So you have decided this is your path. That is the path going to be used. Let me make it so that it is visible clearly. You have decided that is the path, and that's determined by something we call routers. The routers have got they measure certain metrics on the network and make that decision. The routers they make that decision. So in the connectionless communication, that decision is made at every node. In connection-oriented communication, you make that path before you start transmitting. Yeah. But what I was trying to talk about is error correction. So error correction is done This error correction which is done at the link level, which is between here and here, or here and here. So you're going to have error correction between here and here. Error detection, sorry. In fact, in most cases, it's error detection, but it can also be error detection and correction, even between here and here. Yeah. But most systems will also employ error correction between here and here. Yeah. So you can have two error corrections or detection methods or error control methods, the general term, at the link level or end to end. This is end to end. This is you here in Kenya, and this here is your uncle in Atlanta, yeah, or Minnesota, or whatever it is. And although I've done only about 6 nodes on your route, in the real system, you have thousands of routers between these 2 points. But we are saying there can be a mechanism at every link, or like today, since we are using fiber and we don't expect any errors to occur, you can just have an error detection mechanism end to end. So you assume packet is not going to meet any problems en route. So, but in the event that it does, you have a simple error checking mechanism. And if you don't expect so many errors, instead of trying to employ error correction mechanisms, which require more redundancy, you can employ simple error checking mechanisms, which requires less redundancy, and ask to retransmit. So we have seen how these can detect, and that's where minimum distance of a block code comes in, because you cannot have, if for example this code, the minimum distance was 1, that would mean you can get, it cannot even correct errors. It cannot even detect errors, which means once an error occurs, it may not, it may produce another valid code word. So to correct 3 bits, to correct 1 bit error, you require to have a minimum distance of 3. I think here it is. Error detecting and correcting capability of a block code. If you have a minimum distance d min, then you can be able to detect 2 d min minus 1 or fewer errors. What it is saying, if your code is minimum distance of 3, it can detect 3 minus 1 or fewer errors. So it means it can detect 2 or 1 error. Yeah. And T correcting is how many errors you can correct. And we are saying you can correct d min minus 1 divided by 2 errors. So in this case, minimum distance is 3 minus 1 divided by 2. So it can detect 2 or less errors. And this one can detect 1 or less errors. Less is no error, so here it just means 1. And this, of course, denotes the largest integer no greater than d min minus 1 over 2. Why, of course, we are using the largest integer is because for this particular case, 3 minus 1 divided by 2 is a whole number. But it may be a fraction in certain cases. So that's why we are mentioning this, the largest integer no greater than d mean minus 1 over 2. In this case, it will always be an integer. In this case, it may not be an integer depending on the minimum distance. So that's why we are talking about. In that case, it will be the largest integer no greater than d mean. What is saying here? Suppose you got 2.5. Suppose it was 6. D mean was 6. You minus 1, it became 5, and divided by 2. So you got 2.5. It means you can only correct 2 errors. That's what this sentence here means. Largest integer no greater than d mean minus 1. You can't correct 3. Because errors have to be, the number of bits must be large, must be a whole number. So whenever you talk about a T error correcting code, it is the code which can correct that. Yeah. Any questions? I was trying to see whether I can finish this. I don't think I can finish this. So there is no point in hurrying. We have time. So are there any questions? Okay, maybe today I can ask some questions. Sagwa. What is humming distance when you refer to code words? The humming distance. Sagwa Clement. Are you there?
Hello. Yes.
Yes. Minimum, not minimum, just distance, humming distance, or just distance. Or when you're referring with respect to code words, what does that mean?
The measure of how different two strings are equal. Length.
Not the length. Because the code words would have the same length. If you generate codes in the same generator matrix, they will have the same length. Anybody can assist? Clement?
I think it's the number of ones in a code word.
Not exactly. You have answered something else. I wanted to ask but this particular one.
I think it is the number of positions they differ. The number of positions with which they differ.
Yes, is the number of positions in which they differ. So whenever you talk about distance, you must be talking about 2 code words or more. When you have only 2 code words, we talk about the distance. When you have more than 2 code words, then you can talk about the minimum distance, which is the lowest distance between any 2 of them. Yeah. Like in our case, we talk about the minimum distance because it's very important. Now I would ask the weight because I think Emmanuel answered the weight. Weight is the number of ones. So I would ask that one. Why is the minimum distance of a code important in error detection? Ogola, Eric. Ogola is the only one answered. Omolo Alphonse. Why is the concept of minimum distance important in error detection in block codes? Who can assist our phones? And as I'm asking questions, you can be posting your registration on the chat.
I think it tells you if a code word is valid or not. If it like has a distance that's less than maybe 3, it's invalid.
Oh, not exactly. No. Okay. Okay, I like that. Of course, if it's a distance less than 3, that itself would make it invalid. Yes, I agree with that. I agree with you. Yeah, but that is not the measure of validity, because you can have some which are more than 3, but they are valid or invalid. Yeah. Okay. Who can try? I think thanks for that trial. Who can try? Yes.
I think it determines the code's ability to detect and correct errors.
Yeah, of course, it affects the ability to detect errors, because if the minimum distance is less, then it means, for example, if the minimum distance is 1, you can't detect errors, because it means one bit error changing may create another valid code word. Therefore, our method of detecting errors does not work. Because to create when you create a valid code word, the receiver thinks what I have received is okay, and it is not, because that's not what was sent. Remember, we are checking whether a code word is valid, but we just don't want any valid code word. We want the code word we sent. So if anything can change that code word into a valid code word, if something can change the received code word, make it valid, and it is not what was sent, then this error checking mechanism will not work. And I think everybody has posted, so you have a nice week. I think we'll stop there. We'll continue.